Okay, my lecture will be fairly brief, and I want to simply say a few things about mathematics and beauty. Often mathematicians talking to each other say, oh, that's a really beautiful result, or this is a beautiful proof, or sometimes, what? This is ugly. So why we say this and what we expect when in beauty in mathematics. Let's see, this one, yeah. So first of all, what is beauty in mathematics? Well, there are many answers. One does not exist. When I talked to, I remember more than once at the parties, people ask me, what do you do? I say, well, I do mathematics. And they say, well, I'm a lawyer. I hated mathematics in college. So for them, beauty in mathematics does not exist. For a mathematician, often it's an absolute. In other words, if I think that something is beautiful, every other mathematician should think the same. Sometimes a relative notion. What is beautiful to me as a mathematician may not be beautiful to another mathematician, and vice versa. Another point of view, just the product of culture. We influence each other, and so we end up by thinking, our thinking about beauty is indirectly, we are not necessarily aware of that, but we are steered by the crowd. Maybe something else. So, first of all, what is mathematics? Well, the Platonic view, numbers, geometry exist in the Platonic world of ideas as absolutes. So beauty is an absolute, belongs to this absolute world. The mathematician, the role of the mathematician is to be an explorer in a world that we access a little bit, but not completely. Well, there's a notion that perhaps mathematics is not so well defined, and there may be more than one kind of mathematics. I think Gödel was in part responsible for this, and Paul Cohen gave, with the solution of the problem of the hypothesis, continuum hypothesis, which leads to two different models of mathematics, in which in one the conjecture of the continuum is true, in other one the conjecture of the continuum is false. And this model, both models are okay, provided the mathematics we do in the model we usually work is correct. But Gödel says probably we'll never, if it is correct, we'll never find out. Well, formalism, mathematics, construction of the mind, and beauty depends on the construction, not just the final product. And sometimes mathematicians say, well, the result is beautiful, but the proof is terrible. So, and can we get the shades down a little bit? Yeah. Okay, so let's move on. There are other views. Well, mathematics, some philosophers view mathematics as just empirical research that is really, okay. Empirical research, so beauty in mathematics has no meaning, just an accessory, but there's no role in mathematics. Postmodernism is based on the assertion mathematics, since we cannot check whether it's true or not, whether it's consistent. Mathematics, there's no foundation of mathematics except for the very, very super simple mathematics. And so beauty in mathematics cannot exist. Social constructivism, this is social realism, this is very popular notion today. And mathematics is a product of culture. So beauty is a product of culture, and you may explain it using Freud's pleasure principle, identifying beauty with pleasure. Okay. However, in the previous lecture, already heard words like symmetry, power, universality, and mathematicians will add also simplicity, elegance. Certainly simplicity appeared also in the Maxwell equations. And so these are 5 things which, not necessarily all of them at the same time, but there are things which are characteristics of beauty in mathematics. So arithmetic is beautiful. And this is arithmetic as painted by Andrea Bonaiuti in the 14th century. It's a fresco, it's a detail of a fresco of the detail is, it's a gigantic fresco. I mean, the whole church is in Santa Maria Novella in Florence. And there are the 7 liberal arts, and the first one is arithmetic. So it was at the time, in the beginning of the Renaissance, you will see that arithmetic was considered a beautiful art, was one of the arts. So mathematics appears in art. Yes? Okay. So appears in art. Here are 2 paintings by Piero della Francesca. The Nativity, you will see the 5 figures here, 5 figures there. Here again the 5 and the 5 sections, and so on. The geometry is not, however, entirely symmetric. You will notice, oops, I pressed the wrong one. This one. This thing, for example, is higher than those. Hello? Okay. And this column is spaced different from that one. So there are dissymmetries which are very intentional, and they help to add to the dynamic of the painting. So that's one example. This also is an important drawing by Leonardo. If you want to see the detail a little more clearly, you have to look at the tie of our speaker. And this is a very famous drawing which has been used and abused many times, and it's a classic by now. But let's move to modern art. Well, this less modern already. You've seen it in the picture before, but this is the whole thing. And is the famous fresco Raphael in the Stanze Vaticane, in the Vatican, and the School of Athens. And okay, this one. It's not working. Okay, so Pythagoras, there are various characters. Here is Pythagoras, and here is Averroes, and here is Euclid, and there is holding the globe is Zoroaster, and so on. And of course, Plato and Aristotle. The young guy is Aristotle. And here is a detail. Let's see. Yeah. Detailed Pythagoras again, and Euclid. And the model for Euclid was a friend of Raphael, and he was a carpenter, actually. So anyway, the beautiful thing. But it tells us the importance that mathematics had in the arts and the prestige, in a sense, that especially Greek mathematics was already at the time of Raphael. This is more modern, and here we have pure geometric figures with pure colors, and arranged, and this was kind of abstract mathematics going into pure geometric forms. And this is the art of Mondrian. If you look at the paintings, actually, you will find that they are, what to say, much more subtle than what you see on the screen. The colors have a very, very subtle variations, and so have the lines and so on. And here is one more recent example in which just arithmetic comes into the painting. And this Jasper Johns, these are he did quite a number of variations on this theme using just the digits from 1 through 0. He put 0 at the end, by the way. I think 0 is the beginning of all mathematics, but all right. Anyway, there are two lithographies of Jasper Johns, and if you look carefully, you will see every number in it, number 4 and number 2, and all the numbers 1 all the way to 0 are present. He did a very large number of compositions of this type. So, but now let's go back to beauty, a little more mathematics. Let's look at constants first. In Greek mathematics, the golden mean, ratio of side of the star pentagon to the side of the pentagon, and pi, unfortunately now is pi, but the really important question is twice pi. If you make a statistics of all mathematical formulas involving pi, you will find that it's almost always 2 pi, a power of 2 pi, not a power of pi. And there is a reason. But let's look at 2 other constants. One is the square root of -1, the imaginary number, which now we have learned is one of the pillars also of quantum physics. And the base E of natural logarithms, which was the first application of finance to mathematics, was the study of continuously compounded interest. Of course, you compound interest at a continuous rate, your rate of interest should be 0, going to 0 at the same time. You balance the two things, you get this number. And so, this application of finance to mathematics has been very successful because the number E appears now everywhere, in every paper in analysis, and so on. The application of mathematics to finance has been less successful, as you probably know, or by experience if you have some retirement account, because of equating money and wealth to numbers. And in doing this, the financiers forgot the first fundamental law of finance. That's called Bombieri's law. Different Bombieri, that was my father, the banker. And the law says the following, don't forget this. Profits are on paper, losses are in cash. He really said this? So perhaps the most beautiful identity in mathematics is Euler's identity, which is a fusion of the constant 1. Of course, it's a pillar of all of mathematics, arithmetic. Pi, or better 2 pi, is the one of the Greek pillars. I, the imaginary number, which is really a flight of genius, of fantasy, to expand the numbers to the imaginary world. And the number e, the basis of the logarithms. And all these four numbers are related by this mysterious relation. And the exponential e2 pi I times a is at the basis of the study, for example, of every periodic phenomenon. So it's also in physics, mechanics. I mean, all these numbers, they all appear all the time. These numbers, here's an example how to express these numbers in an arithmetical way. By the number e, you get these nested fractions, adding 2 ones, and then the next one is a 6. You add 2 more ones, and the next one is an 8. 2 more ones, and then you get 10, and so on, and then you get the number e. Pi is given that way. The golden mean is that other way. And this is an expression that these numbers can be recreated by means of certain recursive operations of simple nature. Some of these formulas are important, others much less important, but they're curious, definitely. Here is another example, the Markov chain. The golden mean is the number which is most distant from all rational numbers. Because if you try to approximate the rational number, it's always greater or equal to 1 over square root 5 divided q squared. So other badly approximate number are this number I studied first few. And there are quadratic irrationals. And you'll see the, let's see, this thing does not work anymore. The number m, 9m squared minus 4 is the today's square root of that. And the m's are this number here. Those are called the Markov numbers. And they can be generated by a recursive operation with forms sort of a tree. It should be a tree, but nobody has been able to yet to prove it's a tree. His conjecture is actually a tree with branches twice. But nobody has proved that it can join back at some point. Anyway, these Markov numbers, they're solutions of this curious equation in integers. But they have appeared in other contexts like four-dimensional manifolds, quantum field theory, combinatorics, hyperbolic geometry, and this kind of surprise appearance of Markov numbers is, I think, is quite beautiful. So symmetry, you have heard a lot about symmetry. It's a foundation of mathematics, physics, and simply you transform objects, formulas, and keep transforming, but it's always the same thing, always is the same concept, as was said in the previous. So you get these continuous groups of transformations, and the study of the continuous ones is the theory of Lie groups, and it's a foundation of a large part of mathematics. So next. However, even non-symmetric things, here is a tiling obtained with two type of tiles. In that case, we had a kind of quadrilateral, a kite and a dart. Yeah, the black one is the dart here, 5 darts together. And this is the kite here. And they form patterns like that. This is a similar situation with two rhombuses. One is skinny rhombus like that, and then these are not kites, but fat rhombuses. But it's equivalent to the other one. Anyway, these things you can tile the plane that way. It's never periodic, but each part will appear somewhere infinitely many times. It's a very remarkable thing, relatively recent discovery. Finite group of symmetries, I will say a few things rather quickly. We already mentioned the Platonic polyhedra. You can move, and they look always the same because all the faces are the same, the angles are the same, and so on. So group of rotation of a polygon is a finite simple group, finite group. Take the dodecahedron or the icosahedron, rotate it and you get it back the same, and the group of rotation is group of degree 60 of 60 elements. It's a simple group, a very important group, and it's basically the simple groups are kind of basic bricks out of which you can construct every finite group. And so mathematicians wanted to find the structure of all these simple groups, and they turn out alternative groups. The first one is the icosahedral group, the group obtained from essentially starting from Lie groups. And then there are 26 strange objects which do not fit into any classification. So I will mention two of those sporadic groups. One is the convoy group. Convoy is left, or maybe was afraid of that. And it's a certain lattice in 24 dimension, certain special symmetries, and if you discard the reflection that sends a vector to its opposite, you get the symmetries is the convoy group. And this is actually this lattice was discovered in the study of error correcting codes. That's applied mathematics. It's communication theory. The other group is the Fisher-Grice group, F1. It was conjecture to exist by Fisher. He figured out there should be this very strange group. Could not prove the existence, but Grice actually constructed it. The number of elements is this number here, which I wrote a this tells me more than this number, by the way. And it looks a horrible thing, so it was dubbed the monster. Well, the monster, if you try to write down the elements of the group in a different way, you can do by tables, row by column, and by n-squared tables of complex numbers. To represent the monster, you must start with at least with this size, 196,883. That's pretty big. I don't think people have, and the number of elements you have already have is more than the number of atoms in the universe. So it's you cannot even write down all of them. So what do you do with that? Well, there was a curious remark. A strange coincidence that 1 plus 196,883 is equal to 196,884. Now there's a function in mathematics called the modular function J of Z, a very important object in this, coming from the theory of elliptic functions, elliptic curves. And you see here this number appearing. So what's the chance that that number is so close to that? So, okay, no, this is a strange coincidence. So what's next? Well, this is the fundamental domain, the modular group, the function J. If you change Z is a complex number here. Consider A, B, C, D integers, and the product AD minus BC is 1. Then a point here can be reflected in one of these triangles or one of those triangles. The domain here is transformed by transformation of this type, say in this triangle here, or that triangle here, or that one. This, of course, is translation. And so it gives the upper half plane becomes partitioned into these pieces, and these are called the fundamental domain. Picture is rather beautiful in itself, but it's a quite important part of mathematics today. And now there are several ways of doing that. You have to divide the hyperbolic plane by the action of these groups, and there's a group gamma 0 p plus, p prime number. And then what you get, you have to identify those triangles, you have to identify sides in appropriate fashion, and you obtain essentially, in some cases, something which is equivalent to a sphere in which you make a number of little punctures. The prime numbers for which you get punctures, a sphere with punctures, are precisely the prime numbers that divide the order of the monster. That is really a strange coincidence. So it turns out it's not a coincidence. One more, John Thomson noted that the next way of representing the monster requires, 21,296,870 squares with each side as that many numbers. And if you add the first three coefficients, you get that. So this is the coefficient of the modular functions, and this is the trivial representation of the group, one element. This is the first non-trivial representation, this time the full group, because the group is simple. That's the second representation. And this is the coefficient of the monster, of the J function. So suddenly this is no longer strange coincidence, and now there's a beautiful theory, first conjectural, and what the relation should be, and then eventually was done by using really very sophisticated mathematics, and this is a really beautiful piece of mathematics. So next, no, this one. Four colors theorem. Any atlas can be colored using four colors so that no two contiguous regions have the same color. This was conjectured by cartographers back in the 18th century. And by the first proof of the theorem was soundly criticized because it was the computer proof. Computer ran for thousands of hours without checking for, how do you know a computer didn't do a mistake? And also, how do you check to put 1,476 different inputs, which were put by hand, including one of the person was one of the son of I don't know whether of the either Apple or Hacken, but he had only 12 years or so, a teenager, and you're not quite sure he typed in the right input. So if the computers say, well, there are no configurations with 5 colors, but if who knows, if you put the wrong input, it didn't check all cases. So there was new computer proof, much simpler, conceptually simpler, shorter computer time is about 20 minutes, and several independent verifications. And now at least people in combinatorics, and I accept that as a theorem. Beautiful, well, some people say, well, the theory is beautiful, the proof is not. Or so. There's mathematicians still looking for a beautiful proof. Geometry. already you saw the buckyball, and now this theorem more general. If you take closed three-dimensional polyhedron without boundary, closed, V vertices, E edges, F faces, there is this relation, D equal 2 minus twice the number of holes. And this goes back to Euler, and the thing is prototype of a beautiful theory describes how space is put together by cutting and pasting elementary pieces. And this is the simplest case, what is called the Euler characteristic, and it's invariant by deformation and stretching. Homotopy theory is the general theory of this thing, is a beautiful foundation for the study of geometric shapes, the spaces. So what is the homotopy class of the universe? Well, we don't know, and maybe someday the physics will answer that. So here already you saw the example of the buckyball. In fact, a convex polyhedron without boundary faces hexagon and pentagons. Edges form a regular graph order 3, has exactly 12 pentagons. And the corollary is a beautiful contribution to this, to sports. Every soccer ball is 12 pentagons. You heard that. No, this one. Yeah. Okay, this is another example. However, this is not a buckyball. Especially this one is really fantastic. This is a magnification of a living thing. It's the skeleton of a foraminifera. And, well, here you see a pentagon, right here. That's another pentagon. And if you look carefully, you'll find this another one, but at some moment you'll find hexagon, hexagon, hexagon. And the whole thing has 12 pentagons. It's really amazing. This is similar structure, but however, I cheated slightly because here you see a square, so it's a little trickier. But the second one, you can see the vertices very, very well, and that comes from real nature. So I conclude quickly with future vision of beauty, because the whole theory is still, everything is conjectural, most of it, but everything is coming together as perhaps one of the most beautiful things that will appear someday in mathematics as a fact. One is begin with the formula of Euler, relating prime numbers to that series, which is quite symmetrical, I mean, very beautiful. And this is what is called the zeta function. In 1837, Dirichlet extended Euler's formula to new functions with chi of n is called the Dirichlet character. I will not say what it is, but the values are in a group of unity or 0. And it's out of those already proved that every arithmetic progression of integers contains infinitely many primes. And by the way, his proof is still essentially the only proof known. There is an arithmetization of the proof, of Dirichlet proof, but in a sense, it's equivalent to his original proof. Anyway, in 1859, Riemann discovers the exact relation, how it can be used for counting primes, or better, the log of primes. And so you have to do this. These are the complex zeros of the zeta function. So the equation zeta rho equals 0 proves the functional equation, conjectures that all the solutions here have complex numbers, a real part exactly 1/2. Well, if you solve that, it's a really beautiful thing, because you will win $1 million. So, yeah, if you disprove it, it's a terrible thing. So you will not win anything. Well, you will have some recognition, but not $1 million. So today, bit by bit, more things have been the class of zeta and decadal functions been extended. There's a general theory, and there is a foundation of the general theory of these objects. And conjecturally, each one of these objects encodes the properties of arithmetic and geometry. So this would be a functional equation or an hypothesis and have certain hidden symmetries, which is a beautiful thing, of course, which I will not describe. That will be another lecture. So functional equation known in few cases. Recently, Wiles and Taylor contributed with the most advanced results, which were considered totally inaccessible, and now some big dent has been made. Ring hypothesis, there is not a single zeta or L function for which is known to be true. The first 10 million solutions of the 10 trillion solutions, excuse me, of the zeta function been shown to satisfy Riemann hypothesis. And one should think that this is incredible numerical evidence, but 10 trillion is not so big, according to our politicians, because our national debt is 16 trillion, which is a much bigger number. Anyway, so we have three different ways of looking at these functions. And Andre Weil compared the situation to reading the Rosetta Stone, which are the laws of in Egypt for religious, all the religious festivities and so on. At the top is hieroglyphics, this in demotics, and the last part in Greek. So one for the priests, and the second one for the Egyptians, for the locals, and the last one for the visitors. They should know the law. So in fact, it's usual to write things in bilingual, trilingual, so everyone should be aware of the law. Anyway, but all three writings describe the same thing. So the three different ways of looking at the zeta and L functions, they really should be the same thing. This identification is still taking part. So there are some steps that have been done. Automorphic writing is the same as Galois writing. Galois writing is motivic. Motivic means geometric. It's a fancy name for geometric. Motivic equal automorphic. All these three things will be the same. And if we can do that, then we'll start understanding what happens in the arithmetic and geometry all fused together. I mean, that would be a